Today we have an episode that I've wanted to do for a really long time.
I think we've been talking about this for at least the last 6 years.
That's probably true. Today we're talking about nonlinear behavior and analysis methods engineers use to understand structures once they move beyond the simple elastic range and start yielding.
Earthquakes are probably the first thing many engineers think about. Often, our seismic systems are intentionally designed to yield and dissipate energy during a major event rather than remain completely elastic.
Exactly. Many years ago, I worked with Anurag Upadhyay at a consulting firm in Utah where we spent a lot of time evaluating structures for seismic demands. Before that, Anu had completed a Ph.D. that focused heavily on nonlinear analysis. Every chance I got, I was asking questions and trying to learn a little bit about how these methods worked. I don't want to spend too much time defining the terms here. I'm not great at this anyway, but we cover the fundamentals at the beginning of the interview. What nonlinear analysis actually is, why engineers use it, why they should maybe more, what value it provides beyond traditional analysis methods. So, let's jump into the conversation and learn everything we can about nonlinear analysis.
The Structural Engineering Podcast.
Well, Anu, welcome to the Structural Engineering Podcast. We're super excited to have you on this week. This topic is something actually Max and I have talked about for a really long time, just out of curiosity. I know you guys have become friends over the years. You started working together many years ago, and Max brought this up to me, nonlinear analysis, pushover analysis, and said, there's a guy I'm working with named Anu, and he's trying to show me this, and I think I'm going to learn it. And I'm like, Max, what are you even talking about? So I'm so intrigued and I am so excited we finally made this happen.
Yeah, thank you. I'm happy to be here. And yeah, it was a crazy time. I was really crazy about nonlinear analysis or learning. I didn't know much about it at that time when Max and I were working together. And I was like this.
So I only learned the light version and I still couldn't do it. This is a good start. Was this your PhD was based in nonlinear analysis or adjacent?
It was, yes. My PhD research focused on bridges or using BRBs in post-tension bridges with rocking columns. So I created a detailed model of a 3D bridge, like 5-span long, and ran like thousands of nonlinear time history analysis on that to come up with like what's the average behavior of this bridge and how can we provide some kind of assistance to the designers, because not everyone knows how to run these analyses.
Yeah.
So we came up with some graphs and equations to kind of predict how much post-tensioning you should be using, and the columns, aspect ratio, and all those stuff.
That's a very fun application of nonlinear. In general, so Zach and I had thought about questions, what we want to be able to ask you and learn from you here. But most recently, as I was driving home, actually, I really don't understand the basics. And I think the larger audience of structural engineers project what nonlinear means to them in like those two words, but don't really get a good grasp of the very basics. So I'm wondering if we can start on a baseline of pushover analysis, nonlinear analysis. How do we define these things? I can ask better questions, but we can start on that side. I think that might help me learn how this works.
Okay. Yeah, so structures, they are not linear elastic all the time.
Okay.
If you push them enough, they will show some kind of nonlinear behavior. And it's true with everything, right? If you, take a plastic bag and stretch it, it's not going to just rip off, right? I often tell this example to people, like, assume you are carrying your trash bag and it's really heavy because, you got miser on putting another trash bag or just you kept stuffing it. And then while taking it to the garbage bin, you're seeing like, okay, it's stretching because it's heavy, but it doesn't rip, right? Because it has that plastic behavior in it. And that stretching phenomenon gives you enough time to just quickly run and then dump it in the trash bin. So weird analogy, but then we want structures to behave the same way. When the earthquake happens, we want structures to slowly yield, slowly fall, not just like quickly collapse. It should give you ample time to react to the earthquake. Either you hide or you run out. We want that kind of behavior from the structures. And that's why nonlinear behavior is important. Materials in general, a lot of structures, we have like concrete structures, right? They are mix of concrete and rebar. Steel by nature is plastic. It does not just break. Concrete is not plastic. It's brittle. and it just breaks instantly. So that's why reinforced concrete structures can achieve that nonlinear behavior. I should say desired nonlinear behavior. Concrete in itself, if you slowly push it, you'll still see nonlinear behavior, but it won't last long, right? So we should say like desired nonlinear behavior, and we want that behavior. And basically, as of now, steel gives us that desired behavior. So even if we use different materials in a structure, let's say timber or concrete, we want some kind of steel component in there to dissipate energy to show that plasticity behavior in it.
So when we say pushover analysis, is this using nonlinear principles to analyze a building in a certain way to failure?
Okay, so pushover analysis, again, if we just talk in colloquial terms, there's a structure and then you're pushing it over, right? So that when you push the structure, what happens to it? Does it collapse instantly, or does it yield and then slowly you keep pushing, and then it just collapses ultimately? So, right? So pushover analysis gives you the behavior of the structure. It does not give you the demand on that structure. It tells you the behavior. Like, okay, if you provide, if there is an earthquake, the structure will do this kind of behavior. So that's what we use pushover analysis for. Generally, lab testing, the traditional lab testing where we are pushing a structure, a real structure, on one side, that's basically a real life pushover analysis. We did that during my PhD. I did not do it. There were other students who were going through their PhD, and then they would construct like 25% scale replica of bridge models, and then we would push them and then break them and then repair it again, break it again, just to see how many times can we do that. So we do the same thing in a structural model. When we run analysis, we create a structure, we push it on one side, and then the curve we get from the response that tells us the capacity of the structure.
Well, first I'll say I made a lot of 25% scale buildings when I was an architect, and they just fell as I was carrying them when I was in architecture school. So eventually I learned how to go to engineering school, and my buildings don't fall down as much. What is the scale? Like when we have the value from the pushover analysis, like now we know the parameters. What are we adjusting these to based on the capacity we need? And like we'll use generic terms here, but let's say like the building demand from a code sense is the only way I can think about this, is we have 10 kips of base shear seismic. Silly number, but do we want our pushover analysis to be well beyond that and they're just not that related? Or is if you do pushover analysis and it's 11 kips, you're good? Like, I don't know how to even think about the capacity versus demand.
Sure. Pushover analysis is not commonly used for to show compliance.
Yeah.
Right. There are some methods to do it. What happens okay, let's look at it this way. Structure, when they move from from its original position to maybe like sideways, its individual components, they start to deform. Columns, beams, shear walls, they deform, right? It's not the force that's deforming it, it's the overall displacement of the structure that's deforming the components. So the primary aim of performance-based design, or even displacement-based design, that we design components to attain certain deformation. So it doesn't matter at, let's say, 2% drift, if your component still has sufficient capacity to hold up the structure for gravity loads, it doesn't matter how high the forces are. It will still work. So we basically look at the deformation, right? Since traditionally we have been designing structures using force or base shear, we always come back to the same philosophy. Like when we talk about the design, we look at the pushover curve, let's say, then we would say, okay, assume my structure should have R of 4. So my ultimate capacity on the pushover curve is X. My design force should be X by 4, right? That's the intent of ASC 7. It gives you R factor, basically, and then it says that, okay, reduce your forces by this, and then the inherent overstrength in the structure should be able to take you there where it should reach the maximum point. But again, it's a wrong way of looking at the performance-based design. Ideally, you should be running nonlinear time history analysis to get the actual demand on the structures.
Okay. Yeah, I have a lot of questions on that. I got one more quick one, and then go for it.
Yeah, so I'm curious, even stepping further back, just in my own mind, what buildings make sense to do this with? Like I've never started a project because I've never done this before, but started a project and went, man, I wonder if non-linear, is a right approach to this. So like, what's the building look like and maybe the region it's in where nonlinear, performance-based seismic design or performance-based design in general is useful, where it triggers your mind to go, yeah, this is the route we need to take?
Generally, old buildings or existing buildings. What happened? See, building codes, they change, right? ASC 7 has changed. Before ASC 7, it was something else. 100 years ago, it was something else. The codes governing the capacity equation of a concrete column, that changes with time, right? So I cannot expect that using ASC 7 style of analysis on a building that was designed 100 years ago would yield meaningful results. ASC 7 or current ASC 7 equations are based on latest research. At that time, the column confinement concept was not there. Like if the column is standing for gravity loads, it works. So, concrete, how you make or how you mix the concrete, that has changed in 100 years. The steel rolling methods have changed. So the current codes will not produce any meaningful results on such old structure. So we started to look into this nonlinear behavior that, okay, let's test the rebar, what it was. Let's test that steel coupon from maybe a beam or a column, and then create a nonlinear structure or model, and then run analysis. And let's see what happens, right? And then you'll see that that result does not come close to any of these current codes. So most importantly, all the existing buildings, 50 years, 60 years old, they should go through performance-based analysis. It's not design at that point, right? It's just performance-based seismic analysis. And then after that, based on those results, you can design a new retrofit method for them. And those retrofit method using the latest steel should comply with the latest codes. So that's how we mix them. In terms of new buildings, if there's a structural system that is not codified in ASC 7, then you should be using a nonlinear method, a performance-based method. Even with codified systems, one example, if you go to chapter 12 and then look at the table, there's shear wall buildings, but then there's a height limit in seismic design category D, E, and F. Your building cannot be more than 240 feet. If you want a shear wall building with a height more than 240 feet, you have to have a dual system, which is 75% shear wall and 25% concrete moment frame. But that's really expensive. Imagine like 25-story building, you have to put another moment frame in each direction. So engineers started to explore that, okay, we do this nonlinear method for old buildings. Let's try for this new building now. So they showed that, okay, we ran nonlinear time history analysis, and we can say that just with shear wall alone, the building works. Like it satisfies the design intent, which is not more than 10% collapse under MCE level ground motions. So that's how they started to use it for newer buildings. So that the intent was basically to get rid of that additional criteria. But then now any kind of new seismic force resisting system has to go through performance-based design, whether it's mast frames or rocking frames or I don't know, rocking CLT shear walls, anything.
Yeah. So, I've always heard ASC 41 seismic retrofit code is always kind of was the start of performance-based seismic design. Is that true? Can you set a performance guideline and?
Yes, before ASC 41, there were some other codes. It all started with different research groups coming together, writing their own reports. Right, that this is what you do with a concrete structure. This is what you do with steel structure, and this is what you do with foundations. And then at some point, they decided that okay, let's start to codify this process because early 2000s engineers started to use these codes more and more, especially because computation power started to grow. They could run the analysis faster as compared to late 90s. New tools were there. So they started to codify using ASC 41. And that has changed a lot in past 15 years. So traditionally, yes, we would look at ASC 41. And then there were some guidelines for new buildings like Tall Building Initiative, TBI. It's a report by PEER, Pacific Earthquake Engineering Research Center. So they came up with some guidelines that, okay, use these factors and then run this kind of analysis, and this is how you select your ground motions, things like that. And then LA Tall Building Seismic Design Council, they took a detour saying that, okay, TBI recommendations are really generic. Right? Their capacity side equations don't fit very well on the concrete produced in LA region. The admixture is different. I should say the sand and rocks are different. They're different quality. There's different toughness. So
they're saying it doesn't fit as like the statistics standard deviation of the strength or like how we portray the strength and shear and everything of this concrete is not quite the same.
That's correct.
Okay.
So we all the equations we see in any code, they're basically average, right? Average plus standard deviation, I should say, decided by the committee. Sometimes they move away from the average based on the vote, like, okay, no, this doesn't make sense. Maybe we should increase it or reduce it. So that's how we get all those equations and numbers. So LA Tall Building Design Seismic Design Council, they decided that no, we want to create our own equations. So they came up with their own guidelines called LA Tall Building Seismic Design Council guidelines. So any project in LA has to satisfy those guidelines. And they may or may not deviate from TBI. All depends on the peer reviewers. We'll come to that later. So and then after all that, recently ASC 7 added some guideline on nonlinear time history analysis in itself. So ASC 7, now they're trying to consolidate it. They are saying that, okay, it's getting too much deviation from different places. Let's try to be wise about it so people don't get confused and peer reviewers don't get confused. So now ASC 41 provides analysis guidelines for existing buildings. ASC 7 provides analysis guidelines for newer buildings. Moving forward, that will be the intent. And ACI codes will provide component performance criteria for concrete components. And AISC 342 will provide steel component criteria. So you have to look at all these codes together to make sense of your analysis.
I want to jump back with something you mentioned, the 10% probability of collapse. Is that because of material variability that like you have to make it a statistic, or is that also the variability of the applied loads, like what the earthquake is going to shake like?
It's everything. So when we select earthquake ground motions, let's say the code says you have to run 11 ground motions. And then your building may fail for one of those, but for the rest of the 10, it should satisfy the criteria of component rotation, capacity, and overall drift. So that overall drift criteria, let's say the code says that you cannot go beyond 4 2.5% drift or 4% drift. That drift is an average number. It can go beyond that. Of course, the building would fall, but then they have already taken the factor of variability and decided on that number that, okay, if it's more than 4 or 4.5%, we are not sure the building could work, right? So that they've tried really hard to make it simple for people to follow. Otherwise, you would have done like, okay, change this much concrete stiffness to 10% and then see what's happening, or right. So you have to run all like thousands of analysis. So instead of that, they gave you a simplified instruction based on their own research, and then lower bound or upper bound, and then you just follow those numbers.
Actually, I'm pretty sure I asked you this 6 years ago and I don't remember what the answer was, but big picture here, pushover analysis versus a linear, you throw in RISA or whatever. How much stronger, and I know that's a very hard thing to categorize generally, but you know where I'm getting at here is like, if you have a moment frame and you size it in a perfectly linear way and its capacity is 10 kips, we're back to this number, might you see 10.5 or might you see 18 if you did it in a nonlinear, like allow it to yield and see that capacity? And if you don't even want to answer this one because it allows people to be like, well, it's basically the 1.05 DCR, we're good.
Yeah, I mean, see, 1.05 DCR, again, with experience, people with experience will tell you that it's okay.
I
And
don't like it.
it also depends on how critical that particular component is.
Yeah.
Do they feel confident letting it yield? Right. So, or go beyond that number. So if it's really critical, then yeah, you may want to keep it less than 100% DCR. Otherwise, it's okay. But yeah, if you run nonlinear analysis, most of the time things are fine, except for those, like, let's say if there's a critical component and you're saying, okay, 1.05 DCR is fine for me. But then if you run nonlinear analysis, you might see really large deformations in that particular component that could yield to maybe really high P delta forces, or again, could lead to collapse in some of your earthquake ground motions out of 11.
So I'm curious from
Yeah.
that, like from a software modeling standpoint of doing this, how detailed is it getting to be able to, the rotation stiffnesses and things like that? Is it the connections are detailed to a pretty significant point? I mean, how are you seeing what is failing and how drift is accumulating?
In terms of modeling, so we categorize components or their behavior into deformation control versus force control. Like deformation control actions, they can yield. Force control, you don't want them to yield. Like if they yield, you are really at risk of having the structural collapse. So let's say in a moment frame system, the beams are supposed to yield in their plastic hinge zone, right? And then it's basically, we provide a lot of confinement in those areas. So the concrete stays together and then it lets the rebar yield. We don't want beam column joints to yield or crack. I mean, they'll crack, or we don't want it to fail. We call it panel zone failure. So they all have their respective limits. If there's another thing like intent, what is your intent in a structure? And when you design the structure, you have to follow that intent. If your design does not follow your modeling intent, then it's all wrong. If you're saying that I will model my panel zone, beam column panel zone as linear elastic, but then again you're saying that, yeah, it's fine, its DCR is like 1.2, it's gonna yield. No, that's not allowed. If you want it to yield, show us that it's yielding within the limits, right?
Mm-hmm.
If you are modeling it as elastic, then you make sure your DCR is less than 1 in design. So you have to match your intent with the modeling behavior. Wait, did I answer your question? It just maybe I got away.
I think I'm curious too, like which softwares can you do this in? And
Okay, I
then
see.
like, in my mind, building a model in RISA or in RAM, that makes a lot of sense. I do the beams, the columns, the footings, the brace frames, moment frames, etc. So I'm curious of just like what elements are you modeling and then what softwares as well.
Yeah, actually, can I throw in something on the modeling side? Because I was thinking about, as you're saying, connections, right? If we're doing a linear analysis, something we might say it's pinned or fixed, and it is binary. Is there a very heavy detailing component that you need to know exactly how flexible, back to my 10 kit moment frame, exactly how flexible the connection is and how it is shaped so that you know what yields? It just feels like so many layers of detail to model this building with moment frames, push it and say it's yielding okay. I mean, the beam and the column is almost easier in the scale of things. And like you have this intricate connection with lots of plates every way and bolts or welds or whatever. How much time goes into analyzing these connections and like detailing this out?
A lot, yes.
Perfect.
And yeah, it's a really good question. So let's say if you're designing a new building,
Mm,
the guidelines to detail your connections, they're already designed to give you that ductile behavior, right? So if you're saying that, okay, this is my moment frame, this is my beam size, and that's my column, you'll follow AISC guideline to design the connection, the bolted or welded connection between them, right? So it's already documented is in such a way that it will give you that ductile behavior in the beam hinge region. Things get tricky with existing buildings where those existing connections were not designed for that. They did not even follow like pre Northridge moment frame connections in steel, right? They tend to fail really quickly, and that's because of the weld toughness issue. So even though they were looking at the overall intent of the geometry, but then the material they used to connect those geometry did not work well. So there are so many pieces in those existing buildings that are not aligned with the recent codes, right? So uh, it happened to me when I started to work with Mike. Him being this genius in nonlinear analysis, I would look at the structure and then I was like, okay, wait, why do you want to model this connection as nonlinear? It's a connection, we keep it linear, and we just design it's retrofit using those linear forces. But then he would bring up this point that sure, that's your intent, but then now we are penalizing the structure. We are making it stiffer than it is actually, right? So
yeah.
if the beam to column connection is not as stiff as the recent codes, and you are saying that no, it is in the model, your structure's actual period could be, for example, 1 second, but now you're getting zero 0.7 second. Now you're attracting more load. And that's the whole problem with this, like you're kind of going in circles, like, okay, you increased your forces and then now it didn't work. Now you're making it even more stiffer, right? So that doesn't work. So with existing structures, you have to look at the connection. You have to think what it means in having three bolts instead of like whole moment connection,
Mhm.
or what is this riveted connection doing in here? How can I model it? What's the intent? And you decide stiffness based on that. And a lot of times you, let's say you assume a stiffness and then you run the analysis and then you look at the results and then you're like, okay, they don't make sense. The stiffness should be this. And then you do multiple
Very
iterations.
circular. Okay.
Yes. And if you don't have knowledge of all those old systems, it gets really challenging. With new buildings, it's not so challenging because your connection design is following that intent, right?
Mhm.
In terms of software tools, traditionally we only have two software in the industry, at least in the US. Other countries, I'm not sure about. But yeah, both are owned by CSI. And again, for years, I have seen this frustration that they are not developing it further. Codes,
Really?
ASC 47 is changing so much. It has so much flexibility in terms of input that both of these software tools, they're difficult to use with ease. Sure, you can use it, right? But then you might have to spend 2 hours instead of 30 minutes that you should be spending, for an example.
Mhm.
So that's one challenge. Probably um, moving forward, we'll have better tools, especially with AI's help. We'll have better understanding or faster implementation of analysis models.
Yeah. Surprised. Does it feel to you, being in this industry, that it is growing very quickly? Like from the outside perspective, it seems like nonlinear, those words are in Structure Magazine all the time now, and it seems to be becoming more common, which I would assume would lead people that make software, CSI, to advance farther. But does it feel the same for someone that actually knows what's going on?
It will grow and it
Yeah.
should grow. I have seen this behavior from a lot of people that they want to keep the moat for their business, right?
Mhm.
Not sharing too much knowledge about
Yeah.
the methods or even education. I've gone through that, and that's what makes it challenging, right? Like imagine Tesla, electric cars, right? The reason Elon Musk put out the patent for electric cars for free because he wanted to create a market. If there is no market, if there are no there are no competitors, the market will not grow.
Yeah.
So we have to do that, and it's a good thing if people start to use these methods more and more. The more people use these methods, there is more competition, there is more research, there are better tools in the market and better buildings. Right now, per, going through a performance based design is more expensive because, again, it takes more time to analyze a building, and having peer review, which is clunky. Again, we are adding comments in Excel sheets and then exchanging that, and then okay, tracking. Let's say if you have 10 issues in your first meeting, and then in second meeting another issue comes up, and that has to sit between point number 3 and point number 4. Now suddenly your everything, all the point numbers are changed. Now you're tracking. So it's clunky. The processes are still old, and we are not changing. Humans don't change easily. So
Is
there are so
there
many things.
Yeah. Is this software complex enough? So I know a lot of new software products have been placed out recently, and we know AI is helping us quite a bit. Is the software complex enough that it'll lag a small firm being able to develop nonlinear analysis software? Like it still will be in the Bentley CSI suite, or can someone that is very skilled in Python programming in general put something together that gives them a product that they can trust and sell or use with efficiency?
Definitely, you could write your own software or use OpenC's, which is like open source, right? Uh, the See that there is a shared language that people should be using,
Mm.
right? In your office, if you create some tool that uses some language which my office does not use, and then I'm peer reviewing your stuff, how do we communicate that? With linear elastic models, it's easier. As you add more complexity to these analysis models, it becomes challenging to query them. My work as a peer reviewer is to review your work, including your model inputs, your outputs, right? Make sense of them and find out if you made a mistake somewhere. And the intent of peer review is not to point out mistakes. It's actually to help the client get a safe building. That's the intent of peer review. So peer reviewers have this duty that, okay, no, this doesn't make sense. Even if it makes sense to you, even if it makes sense per code, peer reviewers can say that, no, this is difficult. We don't have confidence in it. Let's change this number.
Yeah.
Right. So, and now imagine there are three peer reviewers on your committee. And let's say they have their own tools they created in their office. But then do your tools talk to each other? The same problem we have, like BIM, Revit does not talk to CAD, and then all these things. So instead of that, either in the industry creates an open source thing and then contributes equally. But that's challenging because
Yeah.
not every company has money or time to put towards it. I've seen that. Or you use a traditional software or maybe a new software in future that takes care of all those things, and then you just use it to create your awesome models.
I can only imagine
awesome.
having three people give you feedback on how they would do it or their opinion. And, engineers, although not usually, have huge egos, but they feel confident in what they're doing, right? I think that's an important thing of probably a licensed engineer. So to then send it out to three people and be like, well, I hope they also agree, and to come back with comments.
And see, in the industry, they are not totally unknown to each other. They're not strangers.
Yeah.
They know. I've seen friends like in Seattle, like my team leader presenting our work, and then the other side on the peer review panel, it's his friend there, and then they talk like friends, really freely without any barriers. But then in that peer review meeting, the reviewer is grilling him like, okay, no, why did you do this? Why did you do this? And then after the peer review meeting, he calls him like, dude, what are you doing? But again, we all have our responsibilities, right? As a peer reviewer, they have to follow the intent and their ethics. So I don't think creating software from scratch by every firm is a good answer to this. There has to be a shared language, shared aesthetic to what it should look like. But yeah, individually you can create your own tools. Like, how do you interpret ASC 41 easily or quickly? If you have to, let's say you got a new building project or existing building, it's a weird connection. How do you understand that? In that case, your company's own internal tool could be better than anyone else's in providing you the answers. That's where I think AI will help in those cases, because these codes are so complex and they're growing, and it's okay. Some people hate it, but I think it's okay to have complex codes and better buildings rather than just using the same old methods, right?
Yeah. Could you walk us through one of these projects you've done where utilizing nonlinear analysis significantly changed the design?
I mean, I cannot name the project, but I've seen it over and over, especially with existing buildings. So UC, University of California system, they have their own criteria of rating buildings. So you have to get a seismic performance rating for your building. If you want UC as a tenant in your building, and universities have a lot of money, so clients look forward to it. And then they're leasing for 3, 4, 5 years, 10 years, because when they lease from you, they're gonna set up their research lab or medical hospitals, right? And you cannot move those things easily every year. So if you sign a lease, it's like 10 years or 15 years, who knows? So in order to lease to them, your building should pass a certain seismic performance rating. And it's basically 1 being the best, and you have to have rating 5 or lower. If you're rating 6 or worse, 6, 7, 8, then they won't lease it. And then if you get rating 6, then you say that, okay, no, I'm gonna retrofit my building. Can we still sign the lease, right? So that rating, it's a common project we get at tipping. So a lot of
For
times we
those
have
ratings,
seen that
does it have to be a nonlinear style analysis? Like you can't just look at ASC 7
it
and
it,
chapter
it
12.
does not have to be.
Okay.
It says so we have to follow ASC 41 for that.
Okay.
So ASC 41 provides the analysis guidelines, right? And then there are three tiers of assessment. Tier 1 is basically checklist. If your building is 50, 70 years old, it will fail at least 1 point in that checklist, and then it will fail
Yes.
the intent. Then you move over to tier 2 analysis, which is more detailed. You run some calculations that, okay, this is the shear demand in column, or average shear demand in 50 columns, or average shear demand in 10 shear walls. And then if it fails in that, then we say that, okay, your building did not qualify for seismic performance rating of 5. In in a lot of those cases, we recommend the building owners to run the analysis using tier 3 nonlinear analysis. Okay, give us more time, of course, more money, and we'll run nonlinear analysis. And then I would say, like, in 90% of the cases, it turns out to be a better seismic rating.
Really?
Because now we are utilizing the soil stiffness, or soil flexibility, I should say, foundation flexibility. And then there are so many different pieces in an existing building that the same thing again, we talked about that beam column connection stiffness. If you are saying that it's rigid, you're kind of penalizing your building. But then a lot of these existing buildings, they don't have rigid connections. And then we model them in detail, and then we increase the flexibility in the building and show that the forces are not that high, and the building still works. Yeah, it works. In most of the cases, it works.
Okay. Is there, I was thinking about this earlier, but like when you analyze the building, is there a component that looks at non-structural items like the gypsum on a wall? Especially if you're looking at an old building and how it will perform, is there any wiggle for it will be stiffer even though it's not part of the main structural frame?
Yes. So for existing buildings, we consider all these existing walls to be part of their seismic force resisting system, and we try to utilize their stiffness as much as we can. Uh, we have, again, I had never done that thing before I met Mike, and then he created a program for FEMA that kind of tells you what stiffness you can use for each type of these non-structural walls.
Oh, yeah.
And then he created backbone curves for all of those. So you could actually run nonlinear analysis on a really old, like, say, 100-year-old building, and still show that, yeah, it's not that bad. This building, it could survive a lot of earthquakes, but not completely. But
Yes.
it performs better than you would think.
Yeah. Okay, another one that just keeps jumping way back. When you said the 11 ground motions that you were running across these buildings, where are those pulled from? Are these historic or are these what potential energy is?
Yes, you're supposed to use historic ground motions, and uh, they should be scaled to your response spectrum, MCE response spectrum for that particular location.
Mhm.
And you, based on if it's a near field or far field ground motion, you are supposed to use a certain type of scaling method. There's a frequency matching, and there's a amplitude matching. There are two types of scaling. Uh, we almost never use frequency matching because it changes the inherent behavior of that particular ground motion. Um, because like if let's say Kobe ground motion has a peak at 6 seconds, if you run frequency matching, that peak could shift to either 9 seconds or 3 seconds, and then it could generate more peaks in it because
Mhm.
it's trying to match the response spectrum, right? So that's why we generally don't use that. We almost all the time we use amplitude matching.
Yeah, I was actually thinking that it would have been the opposite because if the site has a higher seismic capacity, the amplitude will be bigger. But in my guessing, like the frequency won't be that different, but maybe it is. I mean, I'm thinking about this totally wrong, but
Good point. So, earthquake scaling or selection, it depends on the building.
yeah.
You your scaled ground motions for a 50-story building versus a 10-story building will look completely different because the span of the periods we are looking at, it's basically we have to match the ground motions should match between zero point 0.2 times t1, which is the first period, to 2 times t1 roughly, right? So 50-story building, very high period, it's the range of interest is different than the 10-story building. So you might get different ground motions for 50-story building versus 10-story building, even though they both are located in San Francisco downtown, next to each other.
Huh.
I'm not saying completely different.
Yeah.
Out of 11, there might be like 6 of them might be the same, and then rest of 5 of them could be different.
Does the group do you kind of know which earthquakes these are? Like in the community that you're in, we'll say, this is the Loma Prieta one. It didn't do that one well. Like, is there an awareness of what this ground shaking was captured from?
There is, yeah. If you miss if you miss those ground motions in your selected suit, you'll get questions from peer reviewers
Yeah.
like, why is this not there? Because if there's a again recorded ground motion data from San Francisco earthquake or anything local, they want to use it.
Yeah.
You
How-
may not always have 11 ground motions from your same location.
Mhm.
And
Yeah, I imagine
let's say
that's kind of rare because how long have we been able to get accurate ground motions read in a computer? Like Loma Prieta is 89, late 80s, 87. I don't know.
October 17th, 1989, magnitude 6.9.
We would barely be able to get information from that. Like, I doubt there were that many precise monitors, and we haven't had that many quakes in the US. So to use that movement, I don't know.
that's true. Another thing was, so let's say Loma Prieta, right? As you said, there hasn't been so many earthquakes. Now, when you run a search in the database, it will give you 6 different records from Loma Prieta, along with 50 others, right? Some of them are from the US, Japan, Italy, or some other places, Turkey. But then the code says that you cannot use more than 2 records from the same event. So you cannot use more than 2 records from Loma Prieta, because if you're doing that, now your analysis has this bias.
Yeah.
And that, as you said, that Loma Prieta recorded data may not be accurate, right? So if you use too much of that, now you're analyzing your building for the wrong ground motion that may not be accurate, right? So you have to distribute your, I don't know, like distribute your ground motion or acceleration or the frequency, all these things. That's why you have to use different events all around the world.
Yeah.
I have a very silly question to ask. We're talking earthquakes, and the taller the building, the longer the period. Often wind is what's governing the design of really tall buildings. Is there any level of design of wind or performance-based wind type of design for nonlinear in that aspect of validating Max and I just last week were on the top story at a restaurant of a 72-story tower in low seismic, so very likely governed by wind, to analyze tall structures?
Yes, they're working on that. So as you said, yeah, most of the cases wind governs that design for really tall buildings, but you still have to check for seismic.
Yeah.
You let's say in San Francisco or anywhere in California, you have to show your compliance with seismic and wind both. There are some places, let's say Philippines. We designed a few buildings in the Philippines when I was in Seattle. It's high seismic, high wind region, and almost all the time wind governed the design, but then we still had to show seismic compliance using nonlinear time history analysis. And we still would have to tweak the design because we would see some failures in there, right? So because wind excites just predominant periods,
Mhm.
earthquake excites a lot of those higher modes. So you will get really different results from both of them. And then you can design for wind, but then if you design for wind and then let's say there's an earthquake which has really long period, goes like a long wave, your building may be fine for that. But then if it shakes really, intense, then it's going to excite those higher modes and then your building may not be fine with
Yeah.
that kind of shaking.
And you're
In
just
terms of,
hopeful that they're both
oh yeah,
not happening at the same time.
sure. Maybe sometime in future. And what was that movie? Armageddon type movies.
Yeah. Yeah, I think Max and I talked about this before. My sister was in Japan at one time and they had a fairly large earthquake during a typhoon. And so it was like over 100-mile-an-hour winds during a 5 or 6.0 earthquake. And Max and I were just brainstorming through what the loading on that building may have looked like. And yeah, interesting thought, I guess.
Wow. I would just assume that Godzilla is coming at that point.
Yes.
Right.
I believe she was texting me at like 3 a.m. her time saying, "Are we okay? Are we safe?" And I was like, "I think you're probably okay." Yeah.
Dinosaur's the problem.
In Japan, probably safe.
Yeah. They've got some very good
Yeah.
design processes there. So
But yeah, to your point about that performance-based design for winds, that's also coming up. There has been a pre-standard for that, and MKA also designed, or I should say, tried to design a building in Texas. And yeah, that design went through peer review process and everything else. And they are trying to promote it more. We'll see more work towards it in the future as we get more and more typhoons. The one thing we see is that the criteria will be really different. The component criteria of satisfactory performance is different than seismic, because seismic happens once every 500 years, right? It's okay for building to just like not work after that. It's not okay if if you think about the humanity, but then in terms of finance, it's okay. You don't have to design such a strong building that withstand that kind of shaking. Typhoons, they come every year, so you cannot have that much damage in a building every year. So you have to adjust your criteria. Like, what should the building do in typhoons that happens every year, or maybe once every 10 years? So we design buildings for 50-year wind, 100-year wind, right? 10-year comfort wind. So there are different criterias for that in that performance-based wind designs pre-standard. And how you model things also changes. So all these modeling backbones, let's say when we are modeling a beam hinge, we are telling the software that this is the backbone of the beam hinge. You follow this, and then it just goes in cycles. And that backbone behavior comes from lab testing. We constructed beams, columns, we tested them, cyclic pushover analysis or testing, and then we gave it to the software. But then typhoons don't cause that much deformation in a beam or column. So the testing has to be different. The testing cannot go to 2% drift. It has to go to, I don't know, like 0.1%, and then see what's happening in terms of nonlinearity within 0.1 or 0.2% drift. It's really difficult to quantify that, right? So you need better methods to look at the data or look at the damage. And then you have to model your structure using that input. So seismic inputs won't work for performance-based wind design.
Gosh.
So
Yeah.
all the more there's more need for better tools that can assist with all these things.
I would say you have gone to school for a long time. I've gone to school for less time in the education of doing one of the, doing a nonlinear analysis. Is it tangible for people that are interested in doing this? Maybe let's like bachelor level or associate. I don't know. How accessible is a nonlinear analysis if you understand the principles behind this, but maybe not, you can't do this, program your own computer to do this. Can people reach this?
Of course, I think one thing they will need is deeper understanding of how structures behave, and they should think beyond this linear elastic world, right?
Mm.
What happens if you deform a component too much beyond its like cracking stiffness? And what happens then? And then what happens in a structure if five beams on the south end yield? What happens to the rest of the structure? So, in a way, nonlinear analysis tells us the story of the structure. Like this happened here, and then 5 seconds later, that thing happened over there. It's not just like, okay, these five beams have a DCR of more than 1.1, and then the structure doesn't work. It's
Yeah.
not that. It's a story. You have to understand
Like
what's happening.
Yeah. Is how
So
like force
as long
and
as
stress moves through.
yeah, and as long as they understand that, I think it's really easy to learn all that. You don't need a PhD or another master's for that. A lot of our industry leaders who are peer reviewing projects all around the US, they don't have PhDs.
Yeah.
Mhm.
They have just worked long enough in the industry with their curious mind that they understand that things are not linear, and it's okay for things to yield. And like if I create a model, run the analysis, show them the results, they'll come up with like 50 points like, okay, no, why this, why this, why this. If I say no, ASC 41 says this, you have to follow this backbone, they'll question that, like, why do you think that's there? Can you change it? With peer review process, you can do so many things. You can change. You don't have to follow the code. Of course, for legal reasons you do, but then the peer reviewers should also agree. If you want to change, you can change it. If they agree with you, like, yeah, you're right, this number should not be used, this beam can deform beyond this point, well beyond this point. And it has happened. I've seen it.
It seems like
Yeah,
there's a
Max
better peer review relationship in this type of analysis than a completely linear. You review a two-story building for the city, and you say your anchors are only embedded 1.5 inches. What are you thinking? It's just, everyone's just angry at each other and uses bold letters.
I mean, that can happen anywhere. I think it's because this performance based seismic design group is really small, right? So they
Yeah.
all know each other
It's a tight
very well.
operation.
I have seen people exchanging ideas. They like, okay, like if I get a project and then I'm stuck somewhere, I can call and ask like, okay, do you have any idea what did you guys do when this happened? And then people are generally nice. They share their own experiences. It's not like they're trying to hide it.
Yeah.
And I think they also understand that we need more people doing these kind of stuff. And more than running the analysis, they need more people who understand this deep behavior of structures.
Yeah.
And that's how you can come up with new bold ideas of like new kind of structures or seismic force registering systems, right? You can create so many.
Yeah, Max and I were just talking about it the other day. Is like I started my career on the West Coast in the high seismic world, and the way people discuss buildings and how they act, I think, is significantly different than I found in the Midwest, because they think more of like, how are things going to move and yield, and there's more of like talking to the building as if it's a person. Like, well, it wants to act this way, or it's going to move this way, or it wants to have this happen, and I find sometimes using that language, because that's how I was taught to talk about buildings. People are like, I don't think the building wants anything, and I always just find it funny. So I love that you said that. Of you really have to understand how the building's going to act, and it's going to do these things. And I think when you think more linearly, you don't have to think beyond that limit, and you're just like, yeah, it hits below 1.0 and we're good, and okay, we move on. So yeah, I like that way of thinking.
No, you're right. Yeah, you have to respect the building's will to move, right?
Yeah.
It's imagine your car's steering wheel or wheels are not aligned, and then you leave the steering wheel and then it keeps trying to go off road, right? And so it's car's will. You cannot do anything about it. What you can do is understand why it's doing that and then fix it.
Yeah.
So it's the same thing. And a building has its own will based on how you design it. You put really rigid coupling beams in a shear wall structure, you're going to see a totally different movement and failure pattern as compared to if you let them yield nicely.
Yeah. Well, I think I've definitely learned more than I didn't know where we're going to go. And I now have a way better understanding of all this. Not that I can run the analysis, but I think it makes a lot more sense to me of the application of it. Is there any questions that we haven't asked yet that you think would be important for our listeners to know?
One question I think one time Max discussed about coding, and if structural engineers, they should be coding or...
Anu and I spoke at the exact same time, so I'm just going to repeat it. He was just saying that structural engineers really should be learning to code. It's giving us a great resource to use.
I think they should. I think the time is changing. I used to code when I was at Dunn Associates, right, with Max. I used to code with Python. Things are changing now. The way coding works now is like you just tell the AI that this is what you want, and then it codes it for you. What I imagine a future where you can create tools using AI, and that's a different thing. You will need an understanding, and you have to code that understanding in terms of, let's say, standard operating procedures. If, let's say, you have an AI to help you, the AI doesn't have its own mind, right? It's trained on a really large data, which may or may not be your office's procedures.
Mm.
If, let's say, Zach wants to have an AI assistant, and Zach expects it to come up with solutions or like codal provisions of particular for a particular problem, it needs to understand that language, and right now it does not. So for Zach, coding would be, how do I program that operating procedure for my AI so that it can grab that relevant information from the code for me, right? So, and for that, Zach's coding will look really different than what Max would code in terms of text. It's basically, at this point, it's text. Zach is writing a PDF or a Word file with like, okay, AI assistant, do this, go to chapter 1 or go to chapter 5 and then look at this section. So he doesn't have to look at those things again and again. Max would write totally different things. So now you're both have created different code, and then AI assistant could come up with different plans in that way. So I see the coding changing now, even in terms of analysis models. Imagine a tool where you don't have to write Python code to like grab all the peak story drift for me. Like if else loops and then trying to call the APIs. No. Now you should be writing that every time you run the analysis in plain English. You can write every time the analysis is run, grab maximum nodes on all these stories, and then only look for these nodes, right? It does not have to look for 1,000 nodes on every level. It should know what nodes to look at, and then it will again write its own program in the background. So I see the coding changing now in that terms, but then it's also good to know how to use either Python or C# at this point, because we are still transitioning from this whole manual coding to vibe coding, or no coding at all.
Yeah.
That's the intent. I'm working on a tool that lets you do that, maybe in future. So I really wanted more and more people to use performance-based design, and then it should not take so long to create a model and then look at your results. I've seen so many companies struggling with that. Again, traditionally structural engineers are not so tech savvy that they can write codes or even understand what those API calls are. So I think that should be the future, where structural engineers can focus on designing better buildings rather than writing codes. If you do both, then it's good.
Yeah. That makes a lot of sense. Well, thank you, Anu, so much for your time and having the discussion with Max and I. Over probably the last 6 years or so that Max has been telling me all about this, I have personally been super intrigued and interested. And I think at some point we maybe have to jump on a call and share screen and you walk me through what you're doing, because I have an idea built in my head now, but I would love to see what it actually looks like on your screen. So hopefully in the near future we can have some time to do that. But thank you so much for your time, for being on the Structural Engineering Podcast.
Yeah, thank you for having me.